Hello, my name is Jett Strack, and I'm an undergraduate here at Northwestern University, and today I'll be presenting on parallel computing in forest fires. Specifically, this will be an overview of a research paper called EFF-SIP, or FSIP, which stands for Efficient Forest Fire Systems Using Internet of Things and Parallel Computing by K.M. Jabir and AAA Al-Khatib. This system combines environmental sensing, real-time analytics, and parallel computing to monitor and predict forest fire behavior. Let's start with the basics. What is parallel computing? Parallel computing is a method of computation where multiple tasks are executed at the same time. Instead of solving a problem step by step on a single processor, it splits the tasks into smaller subtasks and processes them simultaneously using multiple processors or threads. This leads to significantly faster processing and is widely used in fields with massive datasets. Think climate modeling, simulations, machine learning models, or, as we'll see today, forest fire monitoring and detection. Now, on to the problem that we're tackling, forest fires. They spread fast and caused widespread destruction. Roughly 90% are caused by humans, and the remaining 10% occur from natural events like lightning, but are just as deadly. Traditional detection methods like satellite imagery, optical sensors, and watchtowers suffer from inaccuracies and limited coverage. They either react too late or generate too many false positives to be trusted. The ideal detection system is low-cost, real-time, and scalable. Now, how does parallel computing and forest fires work together? To prevent forest fires becoming catastrophic, we need detection systems that are both fast and accurate. Environmental variables like temperature, humidity, and wind are constantly changing and are sparsely distributed, making them perfect for parallel computing. It enables the analyzation of temperature, humidity, and other metrics across thousands of data points simultaneously. This means better response time, smarter decisions, and potentially saved lives and ecosystems. Now, let me introduce FSIP. FSIP uses a network of wireless sensor nodes that collect data on temperature, humidity, and the Chandler Burning Index, or CBI, which is a fire risk metric. This data feeds into three parallel algorithms. The first one is detection. It checks for current fire conditions. The second is prediction. It estimates when and where a fire might ignite. And the third is behavior analysis. This calculates where the fire spreads and its speed and direction. By running these in parallel, FSIP dramatically speeds up how fast we can go from sensing a potential fire to acting on it. And this diagram here gives you an overview of how it is processed in real time. It first gathers the data, then it goes to detection. If there's a detection, it does both prediction and behavior analysis simultaneously for the most fast and accurate results. Now, let's talk a little bit about the nodes in the network of FSIP. The nodes themselves are designed to be cost-efficient, resilient to harsh outdoor conditions. They each contain sensors, a power source, and a communication hardware, all protected from fire and weather with bubble wrap and fire-resistant material. Now for the network, the nodes self-localize themselves using GPS and send their data to a central sink, which is a router running Linux. This router stores the incoming data into a database and sets the stage for parallel processing. So now, let's get into the processing and inner works of FSIP. The first phase is this preparation phase, preparing data in real time. Each thread is assigned a specific task, setting sensor parameters, retrieving data, extracting relevant entries from the database, and calculating metrics. These steps happen concurrently across many nodes. This dramatically speeds up the system's readiness to act on new information within seconds. The next phase is the detection phase. The system identifies whether a fire is actually occurring. It does this by checking whether a sensor node's readings for temperature, relative humidity, and the CBI all exceed predefined thresholds. If all three are high enough, the system suspects a fire, but it doesn't raise an alarm just yet. To reduce false alarms from sensor nodes or local anomalies, FSIP checks the neighboring nodes for confirmation. And here's where the parallel computing really steps in. As you can see with the pseudocode, FSIP uses pthreads to create a thread for each neighbor node. All of these threads are launched concurrently to check if the surrounding nodes are also reporting fire-like conditions. Each thread runs a function called checkNeighbor, which performs the same threshold checks on its assigned node, which are the neighbors. Once all the threshold threads finish using pthread_join, the system looks at a shared variable called fire detected. If any thread is set to true, the system confirms that a fire is happening and immediately triggers an alarm. This approach drastically reduces detection latency and avoids bottlenecks. Instead of checking neighbors one by one, it does it in parallel, making the system faster and more reliable. Now the next phase is the behavior analysis phase. Once a fire has been confirmed and an alarm has been set off, the system switches into analysis mode. This phase is about understanding the fire's behavior, specifically where it started, how fast it's spreading, and in what direction. First, it calculates the location of the first node that triggered the fire alarm, followed by the estimates of the fire's propagation speed and the spread direction. Then it enters a loop to continue updating these values as the fire evolves. In the pseudocode here, you can see how this works. A thread is launched to check if a new alarms are being triggered. In other words, is the fire reaching new nodes? But simultaneously, 3 more threads are launched. One to update the location, one to calculate how fast it's spreading, and another to determine the direction it's moving. All of these threads are then joined, meaning the system waits for them to finish and then updates the values. And if a new fire activity is detected, the metrics are printed and then recalculated for updated information. However, if no new activity is detected, the loop exits. The power of this design is that for each behavior metric is processed in parallel, ensuring that the system stays responsive and up to date in real time. This is critical for decision makers who need fast, accurate data to allocate firefighting resources or issue even evacuation warnings. Now, this next thread is happening concurrently with the behavioral phase. So this phase is the prediction phase. And it's arguably one of the most important ones that is really helpful. Here, FSIP tries to forecast whether a fire is likely to start at a particular node based on recent trends in temperature and humidity. To do this, the system looks at how environmental conditions have changed over 9 time intervals, ranging from 1 minute ago to 2 hours ago. As you can see in the pseudocode, it creates an array of 9 threads, 1 for each interval, and launches them all at once. Each thread runs a function called checkInterval, which compares the current temperature and humidity to the values at that past time. If changes exceed a defined threshold and the CBI is already high, the thread flags a prediction. After all threads are joined, the system checks the results. If a risk is detected, it calculates how long until ignition starts based on the rate of change. It then computes 2 values, min T, which is the time until temperature has hit a critical value, and min H, which is the time until humidity drops to a dangerous level. It then averages these two to get fire expected, an estimate of how soon a fire might start. If no interval meets the condition, the system returns none, measuring no fire is predicted. By analyzing multiple time frames simultaneously, this method gives the system a forward-looking view into what might happen, making it possible to act before fire has even begun. Now, let's look at the benefits of FSIP. The benefits are that it has a beautiful blend of affordability, efficiency, and intelligence. It's low power, low cost, fast, and accurate. By using parallel computing, it shortens the time needed to gather data, detect threats, and make predictions. This can help save from property damage, environmental damage, and even save lives. Now let's look at the results of this research. The system was tested on Dell G7 laptop with an Intel i7 processor, which has 6 CPU cores and 12 threads. Trials were conducted in 3 different environments across the country of Jordan, all in forests. Nodes were placed 2 to 15 meters apart randomly, and real fires were ignited under supervision of local fire authority. In one case, it successfully predicted a fire 28 seconds before ignition. That kind of time could be the difference between a controlled response and a catastrophe. As you can see here in figure 10, you can see where it predicted it and where the real fire was. To conclude, FSIP is a great example of using parallel computing for good. It brings together environmental science and computer science to solve a real-world problem that has major impacts. Future versions may explore GPU acceleration to scale even further and reduce processing time. It is a great example of how computer science can literally help fight fires. Thank you. Here's the reference to the research paper for anyone interested in a deeper dive into it. And then here are my image sources. Thank you again.